Okay, please, Robert.
Okay, thank you very much. Good morning, everyone. I hope you had some good night's sleep and rested and awake already. It's great to have you back for this second part. Just a reminder, I think yesterday it worked really well with the chat. So please use this medium today as well. You can, of course, interrupt at any time. But if you don't like that, please hack something into the chat and I'll keep an eye on it. So today it's our first step towards real nuclear structure calculations for light nuclei as a first start. And I'll just go back to my overview. The two main things that we covered in the first lecture are basic elements of many-body quantum mechanics, a little bit of a summary and repetition to fix the notation and fix the language that we are using. And the second thing is all that we need about the nuclear Hamiltonian. And we had this discussion about different ways to model a nuclear interaction, which is at least 2 + 3 body interaction. And this kind of provides the necessary knowledge to formulate the Schrödinger equation, our eigenvalue problem of the Hamiltonian. And just at the very end of the lecture, I showed you this picture on matrix elements of some of our two-body interactions. And this topic of matrix elements is something which is really, really technical and which you often simply do not find discussed in talks or even in research papers. But it is a very necessary, mandatory intermediate step to go from your general discussion, your general expressions for the interactions and the pieces of the Hamiltonian to the actual many-body world and the basis representations that you use to describe, to solve numerically your Schrödinger equation. So it is often not discussed, but it is a mandatory step. And therefore, I would like to use a couple of minutes to really show you what's behind all that, what the logic is. This will not be exhaustive. It's super technical, but I think it's good to have at least an idea what is involved with this step. So usually the first thing, if you have the Hamiltonian at hand, the first thing that you do is generate what we call relative partial wave matrix element. Relative refers to, we only look at the relative degree of freedom, for example, of a pair of nucleons, not the center of mass. And you want to kind of describe all the information that is in your interaction, in your potential. Think of this argon or some chiral potential into this huge table of matrix elements. So what you need is a basis for this relative motion part of the two-nucleon system. And there are obviously a large number of choices you have there. So invent a basis for the relative motion of two nucleons. That's good to use it. So the question is, what are really suitable or efficient basis sets for our purpose? And at that point, the discussion of angular momentum that we hinted at last time comes in again, because if you use angular momentum quantum numbers to characterize your basis, you have a direct access to symmetries, and you want to use symmetries to simplify the problems, simplify the computation of those matrix elements, and also to simply reduce their number. And this is what's behind this keyword partial wave basis. So we will always use angular momentum quantum numbers and coupled angular momentum quantum numbers to characterize the basis. For example, in two-body space, that can be something like the two-body orbital angular momentum, two-body spin coupled to a two-body total angular momentum J and the corresponding T, so the coupled isospin of the two nucleons. And then you still have some choice to describe the radial degree of freedom, so something like the radial wave functions. There you can pick momentum space. That was a Q that I already showed in these first plots, but you can also use harmonic oscillator wave functions for that. So then you have this extra quantum number, capital N. So this is something that we will use heavily in the first stages of the calculation, namely the step from the operator representation of our Hamiltonian and the interactions to a basis representation. This is only getting more complicated if you go to more than two-body interactions. For example, if you want to do the same thing for a three-body interaction, you need the corresponding basis in three-body space. And this is what we typically call a Jacobi basis. So that's nothing but a generalization of relative coordinates from the two to the three-body system. And this gets scary if you look at just these expressions that I wrote here. Of course, if you have three particles, you can define different relative angular momenta, and you can couple them in all possible ways. So all this stuff here is just the angular momentum spin, isospin information in the three-body system. And then you have two relative pieces of information, which can again be either momenta, these are the Jacobi momenta, or the harmonic oscillator wave functions. So this is getting pretty tricky. And you're doing lots of angular momentum coupling here, but it is a necessary step, and it's an efficient and good step. And this I want to illustrate with the simple example of two-body matrix elements of our potential. And I wrote them again here. So this is again this orbital angular momentum coupled to spin, to a total angular momentum, the isospin part. And here I choose harmonic oscillator basis functions to represent the radial wave functions, the remaining radial degree of freedom. And this is kind of the most general matrix element in this basis that you can write down with the interaction here in the middle, and the bra with this full set of basis states, and the ket with this full set of quantum numbers. And of course, the ket can have all kinds of different quantum numbers than the bra. It's a full matrix. So at that point, you imagine the whole thing as a matrix where all possible entries are relevant and non-zero. Now at that point, because you have angular momenta at your disposal, you can simplify life enormously by simply looking at symmetries. We discussed these basic symmetries like translational invariance, rotational invariance, different other types quickly when we introduced the Hamiltonian. Now it's getting useful because you can eliminate certain off-diagonal combinations of these quantum numbers simply based on symmetry arguments. Not all possible combinations of bra and ket quantum numbers are relevant. That means yield non-zero matrix elements. Many of them actually are zero for simple symmetry reasons. For example, if you look at the total angular momentum J, because this interaction operator is rotational invariant, it doesn't change if you rotate. So that means it's a scalar in our slang. That implies immediately that it does not produce off-diagonal matrix elements with respect to J. So the J prime and the J have to be the same, otherwise the matrix element is guaranteed to be zero. And we call that that the interaction does not connect different J because of spherical symmetry. It's the same for the M quantum number. Also, because of spherical symmetry, it doesn't connect different M quantum numbers. And in addition, the matrix elements are independent of this M. So you simplify life enormously with respect to these angular momentum quantum numbers. And you can go on with this list and consider different other symmetries. For example, spatial inversion, just point symmetry gives you that different parities are not connected. You don't connect different spins. That's also a result of rotational invariance. And you require also some symmetry in isospin space, which means that you don't connect different T and different MT. With all of this taken into account, you know before doing any computation of a matrix element that from all these different primed quantities here, only two survive. These matrix elements can only have off diagonals with respect to these quantum numbers for N and L. This is the only stuff that is left. Otherwise, all the rest, bra and ket quantum numbers have to be the same, simply because of symmetry considerations. Think technically, think in terms of, you want to store this matrix. You have to allocate space on a computer to store this matrix. If you have this information from the beginning, that allows you to devise a much more efficient storage scheme, and it allows you to compute much fewer matrix elements from the beginning. You don't have to compute all these zeros because you know they're zero to start with. So this is really a measure of efficiency to exploit these symmetries. And that's only possible if you go to this angular momentum representation. And that we will always do. And it's even more important if you go to three-body interactions. I don't show you the expressions for the three-body forces here because they're extremely lengthy, tedious. But without the symmetry reduction, you would not be able to store a meaningful set of three-body matrix elements. There would be too many of them. So it's really mandatory that you use these kinds of symmetry reductions. In the end, however, life is not so nice because these relative matrix elements are not the ones that you need for your many-body computation. Remember our discussion on second quantization. You need some matrix elements of this form in your second quantized interaction operator. You have the single particle quantum numbers, alpha, alpha 2, and primed ones here that enter into your general expression for a two-body operator in second quantization. And if you kind of roll out these alphas and write the quantum numbers explicitly, it looks like that. It's messy, but you have the single particle radial quantum number, orbital angular momentum, total angular momentum, projection, and the isospin projection as quantum numbers which you have to handle. So these are the matrix elements that you really need. Well, from the relative world, the one we discussed with symmetries, that's the stuff down here, to this single particle matrix element world, the stuff up here, there exists a very nice transformation. And just to show you all the beauty behind it, this is it. It looks terrible, intimidating, scary. You see all the goodies of angular momentum physics in there. There's a so-called 9J symbol, a 6J symbol, lots of phase factors. And these things here are something very special. They are called either Talmy-Muschinsky coefficients or harmonic oscillator brackets. And they allow, if you just look at the labels that they carry, they somehow connect the single particle quantum numbers of your harmonic oscillator, this N1, N2 stuff here, with the relative quantum numbers, capital N, that we used before. So this is something in coordinate speak like a transformation between single particle coordinates and center of mass and relative coordinates in the two-body space. So this is something special. And this only exists in simple closed form for the harmonic oscillator. If you pick a different basis, even if it's a spherical basis, you cannot do that anymore. And this is a deep, deep down reason why we always start with harmonic oscillator matrix elements. We love our harmonic oscillator, and this is one of the reasons. You have these explicit closed forms for transformations between relative coordinates and single particle coordinates. And we need that for the production, for the computation of matrix. Okay, here's a question. If a symmetry breaking reference state, deformed states, are all these symmetries still valid for writing the Hamiltonian itself? Yes, so the Hamiltonian always has this symmetry. It's a bit of a trouble then to convert from the kind of efficient basis that you use to represent the Hamiltonian to the basis you want to use in your calculation. For example, if you think of a deformed basis to start with, you can start with a deformed harmonic oscillator. This might be very well justified on physics grounds, but then exactly at this step here, you have to do extra work because This transformation, as I wrote it here, brings you to a spherical harmonic oscillator because you use all this orbital angular momentum stuff. If you really want to go to a deformed basis, you either start from here and convert that to a deformed harmonic oscillator, which you can do. That's another kind of analytic transformation in the oscillator world. But that requires that you have these matrix elements as an intermediate step. That might not be the most efficient way. But if you want to start from here and go directly to the deformed world, a deformed basis, then all of this doesn't work anymore. So you have to work harder. And therefore, many of the really deformed calculations, they use simplified interactions where you can kind of shortcut this initial step, and you don't need to go via the relative basis matrix elements. You can compute the deformed ones directly. If you have a very simple delta type force and stuff like that, you can do that. Okay, good. So this is deep down one of the reasons why we use harmonic oscillator. This transformation stuff only works for the oscillator basis. But now we are good to go. And the simplest problem that we can look at is the two-body problem. And the two-body problem for a nucleus means you're looking at the deuteron. And this is probably one of the problems that you've all discovered and discussed in elementary nuclear physics lectures. I will do it here again in a slightly different way because we want to use our basis representations, and I'll quickly go to something like a no-core shell model calculation from here. So look at this simple ab initio problem, two nucleons and the bound state of them. We write down the Hamiltonian in two-body space. And as we discussed, we can separate that into a center of mass piece, which is kind of dependent on the state of the center of mass of the two nucleon system. Maybe that moves, maybe that stays put somewhere in space. And the intrinsic part. The center of mass piece is only kinetic energy, this TCM, which just is 1/2m, and the center of mass momentum squared. And the intrinsic kinetic energy is 1/2 the reduced mass times the relative momentum squared, plus the interaction piece, which is by construction only dependent on relative coordinates because it is translational invariant. And because you have the separation in a center of mass and an intrinsic piece, you can also factorize the many-body state, the two-body state, in a center of mass piece and an intrinsic piece. And as we discussed earlier, we are only interested in the intrinsic degrees of freedom. So what we do is we just solve the eigenvalue problem for this intrinsic part, which is intrinsic kinetic energy plus interaction. You can put the center of mass part here later if you are interested. It's typically just a plane wave solution. If you have finite momentum, you could also think of a wave packet if you've localized your system. But never mind, this is nothing which we need in order to discuss the standard properties of the deuteron. The properties only depend on this intrinsic part. So we want to solve this thing. And this is simple because after separating the center of mass piece, and you know this from classical mechanics where you do that all the time for a Kepler type problem, for example, it boils down to an effective one-body problem. You only have one coordinate in the game, and that's the relative coordinate, the distance between the two nucleons. So therefore, this is simple to do. And what you would usually do is take your Schrödinger equation, take this eigenvalue problem here, and go to a coordinate representation and write down a real differential equation, a Schrödinger style equation to be solved. We're doing something different here. We use our basis representation. We use our harmonic oscillator basis with all these partial wave quantum numbers. So this is now the relative harmonic oscillator with angular momentum coupling. And we expand our intrinsic state, the eigenstate that we are looking for, formally in this relative harmonic oscillator basis. And we introduce expansion coefficients, which carry all the quantum numbers, and we sum over all the quantum numbers. So this is a huge thing. It's kind of the complete basis of this relative part of the Hilbert space. And these states, we discussed them before, they are just angular momentum coupled states for the relative harmonic oscillator, spin and isospin. So nothing new here. I can again use all these symmetries that I mentioned before. The fact that mainly due to rotational symmetry, the Hamiltonian does not have matrix elements, non-zero matrix elements between many of the combinations of quantum numbers. It does not connect, in our slang, different J, M, S, T, MT, and parities. So that means in this huge superposition here, many of the sums can be eliminated from the beginning because you know that the corresponding coefficients are all zero because the Hamiltonian doesn't address them. It doesn't mix in these configurations. And in addition, you have stuff from angular momentum coupling. You know that the J is related to L and S, and the J can only be between L minus S and L plus S. S can be 1, so this is the coupled spin in the two-body system. So you have a little range for a given J that the L quantum number can assume. If S is 0, it's just one value for L that is possible for a given J. So that means also these L summations here are drastically condensed. And you know you have to use antisymmetric states from our basic quantum mechanics discussion. And antisymmetry in this relative coordinate world is closely connected to the quantum numbers. So antisymmetry implies that L plus S plus T, so the three angular momentum style quantum numbers, have to be odd because the L and the S and the T defines the symmetry under transposition that you have in the orbital angular momentum part, in the spin part, and in the isospin part. And in total, it has to be antisymmetric. And that means that this sum has to be odd, because if one of these numbers is odd, that means in this part of the wave function, you are antisymmetric already. And it's okay if just one of the three is antisymmetric, the other two are symmetric, that gives you total antisymmetry. All of them can be antisymmetric, that's fine as well, but it's important that you have this antisymmetry in requirement in this form that the sum is odd. So this helps you. This helps as soon as you kind of decide what J you want to look at. Because if you fix your J, then you can use these arguments to kick out most of the terms in this huge sum without doing any calculation. Again, it's a symmetry argument. And you can decide on the experimental value for J for the deuteron from the beginning, which would be J equal 1 and positive parity. You don't have to. You can try the different J's and repeat your calculation for different J's and then decide which J gives you the ground state. So that would be the pure theory approach. If we use this little bit of information from experiment that the ground state has J equal 1 and positive parity, and if you use all these symmetry arguments from before, this huge superposition collapses to this. The only sum you have left here is with respect to the radial quantum number, the n. So that kind of builds degree of freedom to shape the radial wave function. But all the angular momentum stuff here is essentially fixed. There are only two options left. We have fixed the J to 1, that's this one here. And then if you use all the other symmetries and antisymmetry requirements, you can conclude that there are only two options for the L. L can be 0 or L can be 2. And these are the two terms I wrote out explicitly. The other quantum numbers are fixed. The S has to be 1 and the isospin quantum numbers have to be 0. Otherwise, you cannot fulfill all these angular momentum rules and the symmetry requirements. So you have these two terms. That's pure L equals 0. Therefore, it's called S wave. And this is pure L equal 2, therefore it's called D wave. And that's the famous D wave admixture in the Deuteron, which is not excluded by symmetries, which is possible. How strong it is, what the value of these unknown coefficients are, this is something we have to determine now from the real solution of the eigenvalue problem. And for the solution, we go with our relative Schrödinger equation, with this H intrinsic Schrödinger equation, directly into a matrix representation, which is given by this basis. So essentially, you plug in this expansion for your eigenstate into the Schrödinger equation, and you multiply from the left with these states again. So that means you go from your Hamilton operator, this Dirac notation representation independent form, into a real matrix form for your eigenvalue problem. And if you do that, so plug this in and multiply from the left with all kinds of brass states with this structure, both for the S wave and the D wave part, then you end up with a matrix eigenvalue problem of this structure. There is a big Hamilton matrix, which is simply given by this matrix elements of these relative harmonic oscillator kets. These are from our basis expansion here, and corresponding brass states, which are from the stuff that you've multiplied from the left. And you have matrix elements that have L equals 0 pieces. You have matrix elements that have L equal 2, L equal 2. And you have these off-diagonal matrix elements which have L equal 0 and L equal 2 mixed. The other thing that builds this matrix, that's just a block structure, this 2 by 2 block structure. Each of these blocks runs over the n and n prime quantum numbers, all the way from 0 to infinity, which means each of these blocks, without doing anything in addition, would be an infinite dimensional matrix. That will not work for the numerical application, so we have to do something about that. But other than this, this is the exact rewrite of your relative Schrödinger equation into a matrix form. The eigenvectors you get in this matrix eigenvalue problem are just the expansion coefficients in your representation of the eigenstates. So that gives you the full information you need to set up this eigenstate. And the eigenvalues are directly the energies. And from the solution of this problem, you would get eigenvectors and eigenenergies, so all the information you can possibly get. And we have to do something about these infinite dimensional matrices. That will not work. So you have to truncate. You have to stop somewhere with your basis. You cannot extend these sums to infinity. So what you typically do is you would introduce a maximum value for this n quantum number, and you stop there. Now, this is an approximation. This is what we call a truncation. And this means a departure from the exact eigenvalue problem that you've started from. So at that point, it's a very well-defined point in our derivation, if you like. You introduce an approximation or a truncation. And it's a very controlled approximation because you can always make it better. If you go up with your maximum number n, and we call that n max, then your basis is getting larger and you approach the full space result in some sense. So you can always go larger to improve your result. And that's one important feature. But the thing is, in order to make this numerically tractable, you have to truncate. We'll come back to this point in a few minutes in more detail. But if you've done that, then you can solve this little matrix eigenvalue problem. And in fancy terms, what we've done here is our first Jacobi NCSM, Jacobi no-core-shell model calculation. It's Jacobi because everything is formulated in these relative coordinates. And it's no-core-shell model because it's a basis expansion in a harmonic oscillator. So we are there already. That's our first many-body method. Here developed and applied to the Deuteron. And we'll generalize this to heavier systems in a minute. But once we've done that, once we've solved this eigenvalue problem, we can take the expansion coefficients and convert them into wave functions. So you can look at the Deuteron wave function, the stuff that you've usually, as a result, in your coordinate representation, Schrödinger equation type treatment. And I've just, for illustration, plotted these wave functions for the argon V18 and the chiral NN interaction here. And you see the characteristic structure. So I'm sure you have seen those wave functions or wave functions like that before. You have this very long extended tail, for example, in the L equals 0, the S wave function, which is just a reminder of the very weak binding in the deuteron. It's just a little over 2 MeV binding energy for the system. And small binding means extended wave functions. This is essentially an exponential tail which tunnels into this classically forbidden region far beyond the range of the potential. The potential itself, in the case of the argon, is 0 essentially from, say, 3 or 4. Okay, thank you. So the potential is 0 from here on. Everything out here is just pure quantum effect. It's tunneling into this classically forbidden region. And this is a huge part of the Deuteron probability that you find out there. Apart from that, you find that the L equals 0 piece has this suppression at short distances. The wave function goes rapidly down if you approach small interparticle distances. Now you might think, okay, am I surprised or am I not surprised by that? If I just think about angular momentum and look in analogy, for example, to the hydrogen problem, the electrons in the hydrogen atom, then I would be surprised because L equals 0 doesn't have a centrifugal barrier. There's no reason why I should have this reduction in the probability amplitude at short distances. If I would do a hydrogen-like calculation, this wave function would go further up and end at a finite value here. So what is making this wave function drop or create this hole? And the only thing that is left here is the interaction. And you remember this characteristic form of a van der Waals type interaction with this strong short-range repulsion. This short-range repulsion suppresses the wave function at short distances. This is kind of an energy penalty that your nucleons would have to pay if they come too close to each other. You have this huge repulsive wall, and that means lots of repulsive energy. And the nucleons don't like that, so they stay out of this regime, which means the probability amplitude is reduced. So this, as we call it, correlation hole, is the first indication of real strong short-range interaction effects, short-range correlations. And this is an important kind of terminology, correlations, for the rest of the discussion. A second type of correlations, so in addition to this suppression at short distances, which is due to the short-range repulsion, is the existence of this D-wave admixture, the second part, the L equal 2 part. You don't have that in the hydrogen atom. The ground state is pure L equals 0. And the reason for that is the tensor force that we also highlighted in the discussion of the interaction. This is responsible for the off-diagonal matrix elements between L equals 0 and L equal 2 pieces and generates this small but important D-wave admixture. And that's also a very specific type of correlations that the interaction induces. And both of these you have to take care of in your many-body treatment. Your many-body method has to be capable of describing these tricky short-range correlations. And that's hard. And that makes the many-body calculation so difficult. It's really properties of the interaction in the nuclear structure case that makes life hard. It's not alone the fact that we have 100 particles or so. It's really the interaction which makes us suffer when we try to solve the many-body problem accurately. So this correlation bit is something which we will dwell on a little further. Maybe I make a short break here and ask for questions before we start discussing a little more on these correlations.
Maybe I have a question.
Mm-hmm.
Namely, I mean, you said before that you are cutting your expansion to n max.
Mm-hmm.
So if you can just make a comment about the consequences, also related to the fact that it would be nice to see your figure in exponential, in a logarithmic plot,
Mm-hmm.
because you didn't comment about the decay of this wave function. You said it's tunneling, but also it's tunneling in a specific way. So I was wondering if you could comment about the accuracy of calculations, the truncation, or the consequences of the truncation. No, a short R and large R.
Okay, so we will come back to this in much more detail. The point is, as long as I'm in the oscillator basis, this truncation in Nmax has several consequences. Number one, the thing that we'll always monitor, and that we'll discuss in great detail in a minute, is how does the energy eigenvalue change if I increase this Nmax? This is a keyword convergence that we are looking at, and I will discuss that in great detail later. If you think about these Deuteron wave functions and these exponential tails out here from tunneling, I think what you have in mind, Enrico, is what does the convergence of this wave function really look like if you increase Nmax using an oscillator basis? And now the oscillator basis, and we'll discuss that also later, has a big problem. You remember maybe from your quantum mechanics that the oscillator wave functions drop off in a Gaussian fashion. So there are some polynomial multiplied with a Gaussian. So this is an e to the minus r squared. The physical behavior of the wave function here in this classically forbidden region is exponential e to the minus r. So the wave function that you have in your basis representation really doesn't capture the physics of the eigenfunction that you describe here very well. You need lots of these harmonic oscillator Gaussians to span this exponential behavior out here. And this is another aspect of convergence, or of this truncation in Nmax, which you have to be careful about, and which shows up in many observables that are not the energy. Actually, the energy converges much better than these wave functions, or observables that are sensitive to the long-range part of the wave functions, such like radii. This is also something we'll come back to. So don't worry if that was too brief or too quick, because we'll discuss that in great detail once we have the proper NCSM formulated. Yeah, but these are important points and these are important limitations, and we'll deal with it later. Yeah.
Excuse me, Professor.
Yep.
Sorry if I actually missed a point over there. You said that when we have the matrix elements are actually for, they're in the whole basis, but we need to convert from the basis to the individual particles using the second quantization principle. And that is the Moshinsky transformation in the case of harmonic oscillator basis. Correct. But did we actually go through the calculation for the Deuteron, or was it not required here? Because I think I may have skipped a slide or two.
No, excellent point. We didn't do that for the Deuteron because we formulated the Deuteron in relative coordinates from the beginning. So here, when I set up my expansion of the eigenstate for the Deuteron, this was just the relative harmonic oscillator basis before the Moshinsky transformation.
Okay.
So I don't need to do that for the Deuteron because I can do everything in this relative world, which is natural for my matrix elements. But this will not be possible anymore if I go to 10 or 20 particles. Okay. So then this transformation is relevant. Good point, because I glanced over that. Yeah.
Okay. Thank you very much.
Mm-hmm. Okay. More questions? Okay. Now, let's come back to this idea or this observation that the interaction induces correlations in our many-body wave function. Let's define what we mean by correlations first. So the simplistic point of view is that correlations are everything beyond the independent particle picture. Independent particle means you have non-interacting particles in some kind of potential well, for example, And you just fill up single particle levels according to the Pauli principle, and you build your many-body state as a Slater determinant of these single particle states. So that means that Slater determinants are the kind of prototype of states that individually do not describe correlations. In a single Slater determinant, if you accept this definition, you don't have any correlations because you've just put in particles independently without interaction, and the eigenstates of this independent particle problem are Slater determinants. So a single Slater determinant cannot describe correlations, but we are lucky, Slater determinants form a basis. If you superimpose many of them, then you know that they span the complete Hilbert space, so they have to be able to describe the physics of correlations. The problem is only that for these short-range correlations, you need very many Slater determinants to describe them properly. So now remember what we did with this Nmax truncation. You cut away space because the matrix is getting large, you cannot handle it anymore. This is immediately a problem in connection to correlations, not for the deuteron. You can beat the deuteron to death if you like, in terms of basis dimension, but it will be a problem for all heavier nuclei. So you are in trouble here, because on the one hand side, these realistic interactions, they force you to consider these short-range correlations in many-body states. But on the other hand, you are working with many-body methods, these basis expansion methods, which necessarily rely on truncated Hilbert spaces. You cannot describe the infinite dimensional Hilbert space numerically. And this truncation typically hinders you in the description of short-range correlations. So this doesn't look good. So there seems to be a very fundamental problem between the many-body approaches that we would like to employ and the problem itself, which requires us to deal with correlations. Now, I wouldn't be here if there were not solutions for this problem. And these solutions are typically connected to unitary transformations. They are kind of the bridge between these two ends. We can use unitary transformations to, in a matter of speaking, adapt the Hamiltonian to the truncated low energy model space that you use in your many-body calculation. And by that, you improve convergence. You can live with finite model spaces without tainting your results. And if you do this step from original Hamiltonian to this adapted Hamiltonian via a unitary transformation, you have the extra goodie that you preserve all the physics that went into the construction of the Hamiltonian to begin with. All this few body physics, phase shifts, all this stuff that you used for the construction of the Hamiltonian, that will be preserved if you do unitary transformations. And that's a great advantage of doing this kind of effective interaction in some manner of speaking by a unitary transformation. So this last point, why do you preserve physics in unitary transformations? That's a really simple thing. The first thing is that any unitary transformation conserves the spectrum of the Hamiltonian. That means it doesn't change the eigenvalues if you solve the Schrödinger equation. If you start from the Schrödinger equation here for your original Hamiltonian H, and then just invent a unitary operator U, and unitarity means that U dagger times U equals 1, or the other way around, U times U dagger equals 1. You invent this unitary operator, doesn't matter how that looks like. Now you just insert in this original Schrödinger equation a 1 operator written in terms of U dagger here, and you multiply the whole equation from the left with another U dagger. So there's a U dagger here, a U dagger here. Lots of U's now in the game, but now you collect stuff. First of all, you label this U dagger HU as your new unitarily transformed Hamiltonian H tilde. So this complete first term is H tilde, and you relabel your U dagger times psi, so this kind of transformed state, as psi tilde. And then this whole complicated beast collapses to H tilde psi tilde equals same energy eigenvalue psi tilde. So this H tilde you call your unitarily transformed Hamiltonian. And what you've got here in the end is the eigenvalue problem for this unitarily transformed Hamiltonian, which has different eigenstates than the original Hamiltonian, but they are connected by this unitary transformation. But the important point is the energy eigenvalues have not changed. So if you now forget about all of the stuff above and just solve the eigenvalue problem of the unitarily transformed Hamiltonian, you get eigenvalues which are by construction the same as for your original problem. So that is the statement, unitary transformation conserves the spectrum. So eigenvalues don't change. That's great. You get the same physics out of the solution of the Schrödinger equation. And it goes further than that. If you think in terms of other observables, not energies, something like, say, the RMS radius of your nucleus. This is not given by this eigenvalue equation directly, but you have to use the eigenstates that you get out of that to compute the radius as an expectation value. And if you do that for some general operator A, can be radius, can be some electromagnetic property, it can also be off diagonal. So for example, an electromagnetic transition from an excited state to the ground state, you always compute that as these kinds of expectation values or matrix elements of some operator A. And in my original world, with the full Hamiltonian here, this would be the expression that I want to compute. Now I again plug in one operators to the left and to the right of this A. I write them in terms of the U dagger U's or U dagger here. And I look briefly what I've got. In the middle here, I have again this unitary transformation of the operator A, which I now call A tilde. And on the right, on the cat side, I recover the psi tilde or psi prime tilde. So this unitary transformation of my state. And on the left side, I have the corresponding relation for the bra. That's just the Hermitian adjoint. So in the end, the whole relation collapses again to this. It's these transformed states, psi tilde, with the transformed operator A tilde, and their equal signs in between. So this matrix element is the same as this matrix element. That means, if I forget again about all of the full complicated calculation with the original Hamiltonian, I just solve this problem, then I can compute any kind of observable from these psi tilde eigenstates, the simple eigenstates, as long as I do the transformation for this operator A consistently. I also do the unitary U dagger A U transformation for this other observable. So I never ever have to go back here. I can do everything in this simplified, transformed world. And that's the power of unitary transformations. You have to be consistent. You have to transform all the operators in the same way. But as long as you do that, you have this unitary equivalence, as we call it, to the original problem that was too hard to solve. Okay? So is this clear? That's a kind of important point, because we use this kind of unitary trick for all the calculations that follows. Okay, so there is a question in DFT. There are some advantages in solving the eigenvalue problem in HO basis and then move the densities to the coordinate states for the expectation value calculations. Is there a similar hybrid basis approach in ab initio methods? Typically, we compute all the properties, all kinds of expectation values in the same basis representation. Of course, you could do that. I mean, we can compute something like a density matrix in our basis choice, which doesn't have to be coordinate basis. And you can convert that into coordinate basis if you like. But typically, we don't do that. Typically, we treat all the matrix elements for all the operators that we need in the same basis representation. Also because we have to do this unitary transformation stuff for all of them consistently. And that is also done in this basis representation. So there's no technical advantage in changing into a coordinate representation towards the end of the calculation, unless you want to really interpret something in coordinate terms. If you want to plot some kind of coordinate space density distribution, then of course you go to a coordinate basis. But just for computational reasons, we don't do that. So we decide on the basis we want to use in the beginning, and then the full many-body calculation and evaluation of observables sticks to this basis. Yeah. Okay, now the question is, what kind of unitary transformation really helps us in simplifying the problem? And there, the key word is similarity renormalization group. That's a mouthful of terminology, but actually it's something very simple. So the idea is you use a unitary transformation that has a continuous parameter attached to this. So my U operator now has this little index alpha, and alpha is a continuous parameter which starts from 0. And for 0, this transformation is just the identity operator, it does do nothing. And you can increase this parameter alpha. And as we discussed a minute ago, you can write down the transformed Hamiltonian then with this U dagger H U. And it now has this extra alpha, so this transformed Hamiltonian is alpha dependent itself. This is just a formal statement. I've not told you anything about the specific form of the U yet, and I don't want to, because I just now use this additional parameter alpha, which we call flow parameter in the slang of a renormalization group. We use this parameter to simply rewrite this explicit unitary transformation of the Hamiltonian in the form of a differential equation. And that's kind of weird at first, but you know this kind of rewrite already. You know it from basic time evolution in quantum mechanics. You know that you can describe time evolution with a unitary operator, the time evolution operator. It's a U of t, time. And if you don't want to do that explicitly, you go to Heisenberg's equation of motion, which is just taking the derivative of this relation with respect to the continuous parameter. And we do the same here. You just take the derivative of this kind of definition of H alpha with respect to alpha. And that's a trivial calculation, if you like. So you have two alphas here, and it's in the product of operators. So you apply product rule. First, you have the alpha derivative of the first U alpha dagger, plus same term with the derivative of the second U alpha. And then you plug in, because you like these U's, another unit operator in the form of U alpha times U alpha dagger. It's unitary, so this is an identity operator. Nothing has happened due to writing this in. And then you can identify your transformed Hamiltonian again. So this U alpha dagger H U alpha is by definition your H alpha. So you write your H alpha here. And you have these bulky things left, these derivatives of the U operator times an extra U. And these things you simply absorb into a new operator, which you call eta of alpha. And you call this operator a generator. It's just by definition this combination of the derivative of a U and another U, one with a dagger, one not. And you can show that this term is equal to this term by simply doing the same derivative game with this unitarity relation. So if you take the derivative of this 1 equals U alpha dagger U alpha, then this 1 becomes a 0. And here you have again product rule. You have twice or two terms with a plus, and these are exactly the two terms that you get from this product rule. And the minus here is just from pulling over one of these terms to the other side where you got the 0 from 1. So this is essentially a new thing that you define. You give it a name, you call it generator, and from this little calculation I illustrated here, you can show that this generator is anti-Hermitian. That means if you take the Hermitian adjoint of this operator, then this equals minus the original operator. That's important in order to make this transformation unitary. But if you just relabel now this clumsy term with eta alpha, your derivative calculation from the previous slide boils down to this. So the derivative of h with respect to alpha equals eta times h minus h times eta. And this is a well-known structure. This is a commutator. So you've shown that without knowing anything about this u, that you can use a differential equation in the form derivative of alpha equals commutator of h alpha with the generator eta alpha. And that's just like Heisenberg's equation of motion. In Heisenberg's equation of motion, the generator is the Hamiltonian itself, and the operator, where you consider the time derivative, is some other observable, my a, for example, but then you boil down to the same type of equation. And this is what we call the flow equation of similarity renormalization group. Very nice name, but nothing has happened. Really nothing went into that except that we start with this unitary transformation with a continuous parameter alpha. And now the physics comes in when you think about this eta, this generator. That's unspecified so far. If you have the u, you can compute the eta via this relation. But now we turn things around. We don't design a u, unitary transformation itself. We design the generator, which is much easier as it turns out. And if you do that, you have a full set of working equations which define this similarity renormalization group transformation. It starts out with this unitary form, same for any other observable O, and you convert it into this first order differential equation for the Hamiltonian and corresponding differential equations for any other operator, because you have to treat them consistently. And you have this relation which connects the generator to the unitary operator u itself, which is just the definition rewritten a little bit from before. And now the thing is, this is the basic formulation of the method. It's as simple as it gets. And now you have a choice to design the generator, this eta of alpha, to do what you want, to simplify your problem with regards to short-range correlations, the things that we identified as a big problem initially. The question now is, okay, what can I do about this eta? And there are different choices. There's one choice which is super simple and super intuitive. And we are going to use that for the start. We'll later discuss other choices as well. And this kind of standard choice is to write this eta of alpha as another commutator, namely a commutator of the kinetic energy, the intrinsic kinetic energy that we discussed, and the Hamiltonian itself. So if you remember back, if you plug in this commutator here, you get this double commutator structure on the right-hand side. Now, why is that useful? Can one understand why this specific choice helps us? Well, one thing that you can work out quite easily is you can think about, when does this differential equation end up with a zero on the right-hand side? Let me go back. So when does this right-hand side commutator term vanish? Because if this vanishes, this means that the derivative of the Hamiltonian is getting close to zero. It stops. It's a stationary point of this flow. It's a fixed point. So your Hamiltonian doesn't change anymore whenever the right-hand side goes to zero. And that's something that typically happens for these RG-type flow equations, and that's something that we call a fixed point. And the analysis of what does this fixed point mean tells you very much about how this transformation works. And you can do that with a simple commutator choice, because already this commutator, the eta itself, will vanish whenever kinetic energy and Hamiltonian commute. Okay, that's kind of trivial. But when do they commute? Well, as soon as these two guys commute, that implies that the kinetic energy and the Hamiltonian have a simultaneous eigenbasis. Or in other words, you know very well what the eigenbasis, the eigenstates of the kinetic energy operator, p squared r. These are plane wave or the spherical symmetric corresponding thing to that. And if the Hamiltonian has the same eigenbasis, then this means that we have diagonalized the Hamiltonian in momentum space. So this was the initial plot of this matrix element that I showed you. The fixed point of this transformation, so the generator vanishes whenever you approach a situation where the Hamiltonian is diagonal in momentum space. And that is the ideal world. You've diagonalized the problem with respect to the specific momentum space representation from the outset. So things are getting very simple. And we can see that in a minute in a simple numerical calculation. I see a hand there. I think.
Yes, it's mine.
Okay.
Can you hear me? Can you hear me now? Or
yeah, there's a lot of background noise, but I can kind of hear you.
yeah,
Yes.
sorry. I will make it quick. It's just that. So if you go back to the previous slide, you have that the third equation, d alpha u alpha equals minus u alpha. Yes. Shouldn't we more express everything in terms of u alpha, as eta alpha is based on really the choice of u alpha?
So
because in the end, this third equation is just du alpha over d alpha equals du alpha over d alpha.
Yeah, the answer is no, because this is the trick in the whole game. You don't want to do that. You could do that, sure, that's perfectly fine. But then you would have to make an ansatz, design something for this unitary operator u. And this is much more complicated, much more difficult than reversing everything and to start out with some ansatz for the eta and then derive the corresponding u from this relation based on the eta that you've chosen. So it's just a different perspective, if you like. And it turns out that this perspective of designing or choosing an ansatz for the eta is much simpler than choosing an ansatz for the u, because the operator for this u that will result from this is terribly complicated, because this generator itself changes with alpha. So imagine again time evolution. This is similar to time evolution with an explicitly time-dependent Hamiltonian. And you know that this stuff is much more complicated than simple time evolution with a time-independent Hamiltonian. So we avoid this complication, if you like, by not designing the u, but going to the level of eta and using the eta as our, say, initial piece of information that you stick in to define what your transformation is supposed to do. But this is a very good point, and I'm happy that we could clarify that, because this is kind of the trivial but important trick in this SRG. There are other methods that design the U. We developed one like that, which is terribly complicated in comparison to this kind of approach. Yeah? So it really makes life easier if you start from the eta. Okay.
Thank you.
Okay, now let's do that. Let's solve this flow equation. And solving this equation means, again, as usual, we have to go to some kind of representation, a matrix representation for the quantities that we need there. So again, we dig out our matrix elements. We don't use these operator equations that I wrote up to now. We go to a representation, again, maybe this relative momentum space matrix elements for the two-body system, or Jacobi three-body matrix elements in an harmonic oscillator representation, which I write like that for the three-body piece. And then my nice flow equation for the Hamiltonian boils down to this ugly beast. It's exactly the same equation as before. The only thing that has happened is that I've plugged in the explicit form of this generator eta, my ansatz, which makes this eta another commutator. I've expanded these commutators, so they are always products of 3 operators here. And I've put everything into the basis representation, and I chose this 3-body Jacobi harmonic oscillator basis here. So it looks ugly, but if you get used to it, you identify that all of the stuff on the right-hand side are just multiplications of 3 matrices. Kinetic energy in this basis representation, so that's a huge matrix. Flowing Hamiltonian in this basis representation, a second huge matrix, and Hamiltonian again, so a third huge matrix. So it's always a 3-fold matrix product on this right-hand side. This is something you can handle numerically quite easily. So once you have the matrix elements, you can evaluate the right-hand side, and you can solve this flow equation as a first-order coupled set of differential equations for the matrix elements of your Hamiltonian. And this is essentially a simple computational exercise. And I put this old-fashioned computer here because this is something we can look at, if you like, in this extra session tomorrow with a specific example for these 3-body harmonic oscillator matrix elements for the triton. You can work on this SRG flow equation yourself, and we'll discuss tomorrow how this is being done in practice. It's very simple, super simple, nothing scary about that. And this is a great benefit of the SRG. It's so simple. You do everything at this matrix element level, and you are even able to do that for 3-body matrix elements, which is exceedingly hard for any other unitary transformation method. You can do that reasonably easily with SRG. And let's look at an example. How does that work? And what I show here are all pictures that you know already. We start with the 2-body problem, the Deuteron once again, and we start with this argon V18 interaction. Here are again the matrix elements in momentum space, partial wave matrix elements for 2 combinations of angular momentum quantum numbers. So this is a pure S-wave matrix elements with L = 0 states on the bra and the ket side. And this is this off-diagonal matrix element which couples S and D. That means L = 0 and L = 2. And I plotted them in momentum representation with the bra and the ket momentum here. And using these matrix elements, I then solve the Deuteron problem. And I show the Deuteron wave functions here. It's the same wave functions that we've looked at before. And this setup is my initial Hamiltonian, and it's my initial value for solving this flow equation. So from here, I really start to crank up my flow equation, my flow parameter alpha. This was alpha = 0, as I mentioned, my initial condition. And now just watch what happens with the matrix elements, particularly here in this off-diagonal wings, and with the Deuteron wave function, particularly with respect to the short-range behavior, the correlation ID that we kind of identified. I will now just step through this evolution. I go forward in my flow parameter. You see the flow parameter alpha is increasing. And you see what happens to your matrix elements and the Deuteron solution. If you just hold for a moment here, this off-diagonal stuff from the matrix elements, it's gone. It has been transformed away by my unitary transformation. And simultaneously, my S-wave component of the Deuteron solution has changed completely. This correlation hole is gone. It now ends up with this kind of Gaussian behavior and goes at the maximum value into 0. So I've completely eliminated the signature of short-range correlations, and that goes hand in hand with the suppression of this off-diagonal matrix elements, which, as we said last lecture already, indicate a coupling of low momentum and high momentum degrees of freedom. This is gone. I've kind of pre-diagonalized this matrix. This was what my SRG evolution is designed to do. And that eliminates correlations. That makes life much easier for the solution of the many-body problem. And you can go on. At some point, not much happens anymore. You see that this little diagonal ridge gets sharper and sharper, but the wave function doesn't change much. So at some point, you're done with evolving. You don't have to go to infinity with your flow parameter. This is more than enough to simplify the subsequent many-body solution. We can do the same with chiral. We've discussed that these matrix elements look different out here, and the wave function looks slightly different. But if you run through that, the same stuff happens. This off-diagonal wings are suppressed, and the short-range suppression of the Deuteron wave function, the S wave, is going away. There's a little more happening. If you look at the D wave, this is now much weaker than before. So you also address this tensor type of correlations. You remove probability from the D wave. That has to do with the fact that this off-diagonal piece here is also shifted or reduced to lower momentum component, and it's getting weaker altogether. This is also helpful for your subsequent basis expansion many-body calculation. Now, this is two-body space. You can do the same in three-body space. And this is important because we want to use three-body matrix elements, three-body interactions, eventually in our no-Cauchy model or other calculation. So you have to do the same SRG transformation at the three-body level as well. And in order to illustrate that, I switched to different pictures. I cannot really plot a three-body wave function in any good terms anymore. So what I show instead is essentially my first NCSM calculation for the three-body system. And that is done like that. We start from matrix elements of our interaction in a three-body harmonic oscillator basis. And again, I stick to this relative coordinates. So this is this Jacobi harmonic oscillator basis that I briefly mentioned before. And I plot here the full interaction piece of the Hamilton matrix. And it looks nice. You see this kind of block pattern. This is related to the arrangement of my basis states here. I sorted them with respect to the principal quantum number of these harmonic oscillator three-body states. That's just the energy quantum number of the three particles in a harmonic oscillator, the total energy at the oscillator level. And it goes all the way from 0 here to 28 here. And each of these blocks, which shows up in the matrix elements, corresponds to one slice of this energy quantum number E. And you see that there is a pattern. You have always this kind of, I don't know whether you see that via Zoom because the resolution is reduced, but you have this kind of nice streaks in here. That's really symmetries again in your matrix elements that you can recover in these pictures. But the important bit is you have lots of off-diagonal stuff. So now imagine you want to use this kind of matrix representation to solve the Schrödinger equation, solve the matrix eigenvalue problem. Then you have to kind of cut out a piece of this matrix up to a maximum energy quantum number, something like that here. And you take this matrix into an eigenvalue solver and get the energy eigenvalues. And this is what I show here. These are just the energy eigenvalues as function of Nmax. And this Nmax is now exactly the cut in your principal harmonic oscillator energy quantum number here. So if you go up to, say, this block 20 and include that and cut here, then this is the Nmax 20 calculation that I show over here. So you see, I stopped much earlier than in my matrix. So this goes much higher. I could have gone further, but I don't need to for this illustration. And now again, we can do the SRG evolution based on these matrix elements. And if I do that, I see there's a question. I'll come to that in a minute. Let's just flip through that again. This is my initial condition. And now watch what happens to the off diagonals of this matrix and watch what happens with my convergence plot on the right-hand side. You see this stuff is gone. It's black now, which means zero matrix elements. So you've eliminated all this off diagonal stuff. You've pre-diagonalized your matrix through the SRG evolution. And at the same time, the convergence of this NCSM calculation. So the size of the matrix, this Nmax that you need to get a stable result has dramatically reduced. So we had to go up to 20 or higher to get the converged result initially. Now I have to go to 10 and I'm done. So that really shows you how much we gain through this extra unitary transformation, this similarity RG stuff. So the questions now, number one is, does that mean the correlation signature was just a mathematical problem and our deduction of short-range repulsion of the nuclear force was incorrect? No. Definitely not incorrect. There's physics in these short-range correlations, and we've just managed to shift this physics away from this short-range repulsion into different terms, different aspects of the Hamiltonian. For example, we've shifted physics, and that I'll discuss in a minute, into three-body matrix elements. Three-body forces are getting much stronger through this transformation. So you remove stuff from this short-range two-body bit, you create momentum dependencies, which is one effect, and you create additional three-body forces, which is another effect. Nothing was incorrect to begin with, and we've lost nothing here as long as we do everything consistently, as long as we transform all the operators that we want to evaluate in the end consistently. Because by that, I build these short-range correlation effects, so to say, into the operators. My radius or my electromagnetic transition operator will look drastically different after this transformation. And the transformation itself and the extra structure in the operator takes care of what the unitary transformation has removed from my wave functions. And I think that is related to the second question. It'd be tempted to think that losing those correlation would mean a lack of physical reality. How is this not the case? That's exactly what I said. You just shift information from your wave function, which is difficult to handle in a many-body treatment, into complexity of the operators itself. Yeah, so any of the simple operators that you know, a radius operator, will look much more complicated after the transformation, and it will have imprinted what you usually would get from the short-range correlations in the wave function. So it's just a change of picture in the language of quantum mechanics, and again, in the language of time evolution. If you remember this Heisenberg equation of motion and Heisenberg picture was just that you put the time dependence onto your operators and you remove it from your wave functions. We do the same here. So you remove complexity and, if you like, information from the wave function about short-range correlations and build that into the operators. You lose nothing because you have this unitary equivalence. Yeah? So these are very important points. Thank you for the questions. Now, there is no free lunch. I think you all know the no free lunch theorem. This sounds too good to be true, what I just said. So there has to be some catch. There has to be some drawback of doing this transformation. And there is, and I'll be very brief on that. You can use, again, our beloved second quantization to illustrate the point. If you just write down this transformation, this flow equation, in a super simplistic Euler type approximation. So you go from the differential equation by writing the derivative on the left-hand side as a difference of the Hamiltonians at a small alpha point, which I call delta alpha, minus the original Hamiltonian. So this is kind of an Euler type approximation for this initial value problem that we are going to solve. If you write that, then you see that the original Hamiltonian is modified in one step of this evolution by this double commutator that makes up the right-hand side of my flow equation. Let's think about this double commutator for a moment. If you have the original Hamiltonian, this H0, this, let's assume, is a two-body operator. And I use this kind of sketchy second quantization here to write this two-body operator with two creation, two annihilation operators. And then I have kinetic energy in here, which is intrinsic kinetic energy, so total kinetic minus center of mass, which can also be written as a two-body operator. Now I put these sketchy second quantization forms into this relation. Then I have my original Hamiltonian, which was two-body, and then I have these nested commutators of all these creation and annihilation operators. What I want to work out is after evaluating these commutators, how many creation and annihilation operators are left? Or in other terms, what is the particle number rank of the interactions that are generated there of the terms? Now, there's one thing about commutators. If you work out this, you might think, okay, it's a product of this operator and the other direction. You might be tempted to think that if this is a two-body operator and this, that the commutator as a whole is a four-body operator. It's not, it's just a three-body operator because the commutator reduces the operator rank by one, but that doesn't matter. If you go through that, you will find that this extra term has up to 4 creation, 4 annihilation operators, and of course 3 and 2. So by a single step in this flow evolution, you generate from an initial 2-body Hamiltonian suddenly up to 4-body interactions. This is the price you pay. You generate, you induce, as we call it, many-body contributions, many-body operators, many-body interactions in your Hamiltonian. So the thing which was initially, say, a simple 2-body Hamiltonian, 2-body force like the argon, gets in each iteration step, in each solution step of this flow equation, multi-body terms in addition. And in the end, it's an A-body operator. So the complexity of this Hamiltonian after flow evolution is increased dramatically. You don't have just 2-body pieces, you have 3-body pieces, 4-body pieces, and so on. And that is hard. It's hard to solve the flow equations at the 3- or 4-body level. We did that, and it's super painful. And it's hard to implement something like a 4-body interaction into a many-body calculation. This is the price you pay. So this is an old free lunch theorem. You get rid of the correlations, but you get complexity and multi-particle terms in your Hamiltonian. And you have to keep them if you want to preserve this unitary equivalence exactly. We cannot keep them all. So here is another truncation, another source of uncertainty in our many-body ab initio framework. We truncate this cluster expansion of the Hamiltonian, and we typically go up to the 3-body level. We stop after the 3-body terms. You might argue, okay, is that a good approximation? Well, we have to show that. And you have diagnostic tools to show how big the effect of the residual terms is, because you can play with this flow parameter. You don't do calculations at one fixed flow parameter, but you compare calculations for different flow parameters. If the thing would be unitarily exact, nothing would change for the energies. So any dependence on the flow parameter indicates that these higher order terms that you might neglect play a role. You have to do that diagnostics. It's yet another type of truncation, which is hidden in the calculation. And for all that we are going to discuss in the following, I'll stick to this level of including all the 3-body terms, but neglecting the 4-body terms, because this is really getting very, very tough. Okay. Now we are ready to do the many-body problem, and we are essentially almost out of time. I will still say a few words to that, because that will be very simple now, but maybe I stop first for a minute or two and ask for more questions. Anything on this similarity RG stuff still open?
Yes, one question. I don't know what's the way you do this 4-body interaction, but can we contract that 4-body operator, 3-body operators into using Big's theorem to a 2-body interaction?
Yes.
And
okay.
May that residual 3-body part are or not?
Yes. So you're an expert. Thank you very much for that question. We will come to that later when we talk about normal ordering, Wick theorem, and the so-called in-medium similarity renormalization group. That's an option. So you can absorb part of these multi-body terms in the evolution into lower rank, say 2-body operators by using normal ordering. But the thing is, you have to implement that at the level of your flow equations directly. It's not helpful to do that afterwards, because the real trouble is to solve these flow equations in four-body space in order to be able to get this piece. So it's not an option to first construct this piece and then reduce it via Wick theorem to lower rank operators. That doesn't help much. You have to formulate the full flow equation in normal ordered form, and then you are at the level of the medium SRG, which we'll discuss later. So this is a very clever thought, and we will do that, but there are kind of two different stages of SRG that are typically done. Also, this normal ordering trick with the medium SRG will not help you if you really start from the initial hard argon V18 type Hamiltonian. So what we are going to do later is kind of a moderate free space SRG evolution. Free space is the variant of SRG that I just discussed, and then use the second stage in medium SRG on top. But we will come back to that, and that's a very valuable thought. Yeah. Okay, more questions? Okay, so just 10 minutes or so for the many-body problem. And we will not need much more because we've done it all. Essentially, you've seen the first calculations already, and these calculations are from a family of methods that we call configuration interaction approaches. And in pictorial terms, configuration interaction calculations always look like this. You construct a matrix representation in a many-body basis of your Hamiltonian. And this matrix I plotted here is actually for carbon 12 to have some specific example. And then you solve the matrix eigenvalue problem of this thing. That's configuration interaction, done. The only question is, what basis do I use for my many-body space, for my matrix representation here? And how do I truncate this matrix? Because as usual, it will be infinite dimensional to start with. So I have to truncate somehow to make that numerically tractable. And these two things, choice of basis and choice of truncation, that distinguishes a whole family of configuration interaction methods. So if you want to set up the general thing, it's just what we did all the time. You pick a single particle basis. For us, it's typically the spherical basis. You could think of a deformed basis as well. You construct a basis of your antisymmetric A-body Hilbert space from that via Slater determinants for all possible combinations of these single particle states. And this will give you a basis in A-body space. And you use this basis to convert your abstract eigenvalue problem of the Hamiltonian into a basis representation. You expand your eigenstates in this basis, which I call phi I here. And you rewrite your full eigenvalue problem as this matrix eigenvalue problem. Exactly what we did twice already for the Deuteron calculation and for the three-body calculation in the context of the SRG. It's a kind of prototypical CI calculation. But now the thing is, what do we do with this matrix here? It's infinite dimensional. The single particle basis, if you think harmonic oscillator, has infinitely many states, and if you build Slater determinants from that, it's only more infinite than before. So you have to truncate. And truncation essentially defines what we call model space in these calculations. You go from the full A-body antisymmetric Hilbert space to a finite model space. And in this finite model space, you do your eventual numerical calculation. There are many ways you can do this truncation. Some of them are better than others. Some of them are complicated. There is something which is mainly in the quantum chemistry community, which uses these methods just as well, which is typically called full CI, which means you just truncate the single particle basis. So you take the first, I don't know, 100 harmonic oscillator single particle states, and then you construct combinatorially all possible Slater determinants from this 100 states. And then you have a basis in your A-body model space and you solve your eigenvalue problem. Would be an option. It's super inefficient. We never ever do that because it's so inefficient. The matrices are getting so large, you cannot handle that. You could impose an extra truncation, something like particle hole truncations. We had this concept already when we discussed second quantization. You can simply define a reference state, the lowest energy Slater determinant, and then do one particle, one hole excitations on top. That would define a very small CI type space, and you can solve the eigenvalue problem. One particle, one hole will probably be not enough. You can go 2 particle, 2 hole, 3 particle, 3, 4, 5, 6. And at some point, you would expect that the most relevant configurations are in there. So this scheme already is informed by some physics. You have the expectation that really a particle, a hole excitations will not be as important as, say, a 2 particle, 2 hole. So this is kind of a way to go. So use physics-informed truncation schemes. And this is something which we will push further. And you could also think of the interacting shell model, so valence space and core, as a specific type of truncation. We'll not discuss that anymore here. But whenever you do that, and whatever you do regarding a truncation, you have to demonstrate what we call convergence. You have to show that the observables you are interested in, energies and any other observable you want to compute, that they are independent in the end of your truncation, that you can push the truncation far enough towards the full Hilbert space limit that your observables don't care anymore about the extra states that you get in your basis if you would go even further. This is convergence, and this is a critical ingredient for all of these CI type methods. There's one degree of freedom you still have, namely you can optimize the single particle basis. We'll discuss that later. Now, I will skip this maybe for a minute and just as a last point, illustrate what the no-core shell model is in this context. The no-core shell model is just one specific type of truncation. It's one specific CI type method. And in the purest formulation, it has 2 defining elements. Number one is the single particle basis is a spherical harmonic oscillator basis. You don't use anything else. And the truncation of your matrix is not a simplistic truncation of the single particle basis, but you use a truncation at the A-body level. You really define a truncation criterion which acts at the level of your Slater determinant A-body states. And you use the total number of excitation quanta in the harmonic oscillator that such a Slater determinant contains. This is illustrated here in this plot. So you see the harmonic oscillator, you see some nucleons put on here, and these are 8 protons, 8 neutrons. So this is a representation of oxygen 16. And you see the single particle energy levels of the harmonic oscillator, this characteristic equidistant spectrum. And if you remember your quantum classes, you will discover there's a mistake in this plot. I'm talking about the 3-dimensional oscillator here. But if you remember the quantization of the energies in a harmonic oscillator problem, you can reconstruct that what's plotted here is a spectrum of the 1-dimensional harmonic oscillator, because this energy difference between the bottom of the potential and the first energy level is 1/2 h bar omega. It should be 3/2. Sorry for that. But the thing is, now you start to build a reference state. You fill in nucleons in the lowest possible configurations, and with the 8 protons, 8 neutrons I have, I can just fill the first 2 oscillator levels. And then I count for all the other Slater determinants of my basis, how many steps in these oscillator quanta I have to excite my individual nucleons to reach a specific configuration. So what I plotted here is not this lowest energy configuration, the reference state, but I have put a nucleon here, here, and here. And now I compare to the lowest energy configuration and add up. This nucleon was moved up 3 steps. This nucleon 2 steps, this nucleon 1 step. So this is a 6 excitation quanta configuration, or an Nmax equals 6 configuration, as we call it. And we truncate in this Nmax, which counts excitation quanta. You will easily convince yourself that something like a situation where all the nucleons are up here, which is possible, is very large Nmax. And you can ask yourself, is that good or is that bad? If I would do this full CI type calculation, and I would include the single particle states up to here, I would have the configuration with all the nucleons up here included. And I would argue, and we'll see later, that it's extremely unlikely that this configuration will be important. What I count here is really, so to say, unperturbed energy in my basis configurations. And this is a very, very sophisticated and physics motivated quantity already. Therefore, we will find that this Nmax type truncation is way more efficient than the other truncations I mentioned before. And efficiency means I get converged results for smaller matrix dimensions in the end. Because I only have configurations used in my basis that are really relevant for the physics description. And these two things is the pure definition of no-Korshal model. And these two things have a number of technical advantages, which we already saw. Number one is this efficiency aspect that I mentioned already. But number two is you can choose two different representations or basis families for writing your NCSM problem. You can use these relative or Jacobi basis states as we did it for the Deuteron, but equivalently, you can go to this single particle basis type thing where you need this extra transformation and where you can use second quantization. Both of them are equivalent. They yield exactly the same results for each and every Nmax. So that's good because for the light systems like Deuteron or three-body system, sometimes four-body system, you can use this relative coordinate formulation, which is more efficient. You have less transformations. Things are easier to handle. And for the heavier systems, you switch to the single particle Slater determinant representation, which is the only way to go heavier. So that's a nice to have. And that relates to another important aspect, and that's, again, center of mass and intrinsic motion. This is essentially the only basis choice, the only truncation choice that guarantees an explicit separation of center of mass and intrinsic motion for each Nmax. So you are sure that this very basic symmetry discussion thing that we did in the beginning is possible. You can separate, factorize the center of mass state for this NCSM type model space. This is not possible if you go to a different many-body truncation or if you go to a different single particle basis. It's a question whether this is really important to have that, and we'll get rid of that later for other methods. But it's a nice feature which only the NCSM with the oscillator basis gives you. Now there's a question, is NCSM suitable for each system, also for heavy ions? And you nailed it, no, it's not. And the reason is simple, and the reason we will discuss next time. It's simply that the basis dimension gets out of hand. Your matrices are getting way too large if you go to heavier systems. And where exactly this starts to become a problem, we will see next time. And we will devise methods to get a little bit further than these limits. But the NCSM, as of now, with all the tricks that we can use, is capable of describing something like mass 25-ish systems. So all the way from 2 to 25 you can do with these methods. But beyond that, the matrices would be too large to handle numerically if you want to reach convergence. That's the point. We have to do large enough Nmaxes, and again, this we will look at next time in more detail, in order to converge all our observables. And this will not be possible anymore for heavier systems starting from mass 25 upwards. Yeah. Okay. I think I will stop here. We are out of time, but maybe if there are more questions, one or two, we can handle that. Okay. I don't see anything coming up. So we will continue with this NCSM discussion next time, coming back to the applicability and also further tricks and improvements that you can do, and also a little bit to the computational aspects behind that, because after tomorrow's lecture, we will have this practical session, and this will deal with the SRG and also with the specific NCSM solution, do it yourself, if you like. Okay.